Hello everybody. Time for another video. I really wanted to get this video out yesterday, but just didn't work out in spite of me doing everything I could. So it's happening today, right now, and it is for what, at least at this time, fall's 2022 semester. It's for the third assignment for our class. Okay. Now before we do the math, I'm sure you're wondering who the cat of the day is. Let's talk about that. The cat of the day is, so this is Salem. And Salem's a friendly cat. He's real nice, but he was extra friendly today. He really wanted a lot of attention. So that's why he's cat of the day. Whoops, that's not what I want. There we go. There's Salem. So I've noticed with the cats, some days they're really withdrawn, and some days they're extra social and they want a lot of attention. And I guess for whatever reason he was in a real good mood today, feeling good, and that's why he's cat of the day. There he is. Anyway, let's go to the math. Now, topic here, is average rates of change. And first I want to give you a formula, and I want to explain a little bit of the terminology that you're going to see going along with the problems. Okay, so an average rate of change. The way that what we're encountered with might read is something like this: the average rate of change for a function. Okay, so let's see. So we have a function, okay, between number A and number B. Okay. So we'll have a function and we'll have two numbers, and we can calculate the average rate of change. Now the wording might be a little bit different than this, but it's going to be a lot like this. You're going to have these three things. Okay, a function, and then x equals a and x equals b. And we'll find also that b will be bigger than a. Okay, so between x is equal to one number and x is equal to another number that's bigger. Okay. Anyway, so the way that you calculate what is called the average rate of change in that case is f of b minus f of a over b minus a. And then from there, you just, simplify this or calculate it, whatever the numbers are. Okay. All right. Now, so that's the formula, and that's the terminology, and so on. Let's look at an example. So here's one that reads just like what I had told you. All right. It says calculate the average rate of change for, okay, so here's that function, right? So we said, like, we'll have a function, and then we'll have between x equals -1 and x is equal to 2. So a function and two numbers, all right? And the way that it's given to us is that first we get the smaller number, and then we get the larger number. All right. So that formula that I just read, so here's my math, but it says that we should do this. F of the larger number, so f of 2, minus the function value at the smaller number, so that'd be -1, so we should do f of 2 minus f of -1 over the larger number 2 minus the smaller number, which is -1. So what you see right here is that formula. Okay, so there it is. That's how that formula would be applied in this case. By that formula, I mean this initial one that I gave you. All right, that one right there. So okay, that's what it looks like in this case. Now, can you see why this is f of 2? All right, well, there's our function. F of x is x squared plus 11x. So if I was to plug 2 into that function, it would be 2 squared plus 11 times 2, right? So can you see right there? Just make sure that's f of 2. And this, all right, that's f of 1. And so that would be -1 squared plus 11 times -1. There you see it, all right? Okay. Right, so I just want to make sure that you see all that. Now, if I do the math, I'll get, here this is 22, and then that's 4, so I'll get 26, okay? So again, that is f of 2. And then So 11 times negative 1 is negative 11, and negative 1 squared is 1, so negative 11 plus 1 is negative 10. Okay, so that's f of negative 1. And then I'd simplify from there. 26 minus negative 10. Well, I'm subtracting a negative, so that says 26 plus 10. I'll get 36. Down here, 2 take away negative 1. Well, that's 2 plus 1. That's 3. 36 over 3 is 12. And then I'm done. That's my average rate of change. Okay, now, so far, I haven't told you why average rate of change. Why is it called that? What does it tell us? There's all kinds of questions that you can have about that at this point, but we'll get there. All right, for now, I just wanted to show you the formula and show you how the math would work out. Okay, let's look at another one, because there are lots of ways somebody could go about this and write this down. Once you have the formula, once you know what it is, there it is. That's how you calculate the average rate of change for a function. Well, once you have that, not everybody is going to necessarily do it the same way. So I'll show you a slightly different way that you could go about it. So let's take a question with similar wording, okay, where I go about doing the math a little bit different. All right, so calculate the average rate of change for the function. Okay, so we said we'd have a function, and then it says over the interval -7 to -2. Well, that's the same information, right? So let's see. Can we agree it's the same information? That I'm given a function and I'm given two numbers, all right? And then the first one given is smaller than the second one given. Yeah, we have that information. It's the same thing, right? -7 to -2. So -7 being a little bit smaller than -2. -2 is bigger than -7. So, all right, same information. It might read a little bit differently and so on, but it is the same. We're working with the same thing, okay? Now, all right, here's what the formula says that we need to do. We take f, the function value at the larger number, -2, minus the function value at the smaller number, that's -7, over the larger number minus the smaller number. It's that same formula that I started the video with. Now, what's different about it this time? Well, this time, instead of doing all the math within the formula, I thought, well, we could do the math separately. Like, what's f of 2? Instead of writing down how you calculate that up here, I could calculate that and all those numbers on the side, okay? So as long as you understand, all right, here's our formula, I need to figure out what all those numbers are, I can do that however I want to go about it. So what's f of -2? You take this function and put -2 for x. Well, there it is, all right? And here's what you get. Ultimately, we get -6. All right, so I'm going to get -6 right there. Then I'm subtracting, you see that? And then I need to figure out what's f of -7. Well, I'll do that down here. So f of -7, what would that be? I would put -7 into this formula, which would look like that, which would reduce to this, 6 divided by -6, and that's -1. So I need to do -6 minus -1. F of 2 minus f of -7. F of -2 minus f of -7. Okay. So, all right, I got that. That's what I needed. And then I'm going to just recopy this. I'll do it in the next step, but you could do that however you want it. All right, so let's see. I'm going to get -6 minus -1. That's going to be -6 plus 1. That's going to be -5. Okay. And then this is going to be -2 plus -7. That's going to be, -2 minus -7 is -2 plus 7, which is +5. All right. And then that's going to be -1. So there's our answer. Now, I showed you two different ways because, I'll give you that freedom. If you realize this is how the average rate of change is calculated, how you do the math from there as long as you get all the right numbers and so on, it really doesn't make that big of a difference. Okay. One thing, before I leave this particular aspect of it behind, that people sometimes miss is if we have a, a lot of negative numbers in this formula. Sometimes people get lost with all the negatives. You see how the average rate of change has a built-in subtraction right there and another one here? It's just part of the formula. Well, keep in mind that you're going to have that in addition to whatever negative numbers that you have when you're doing the math. So here's what I mean. This subtraction is part of the formula, and must be carried over and applied to whatever numbers you have. And same thing with this one. It's part of the formula and must be carried over and applied to whatever numbers you have. All right. Now let's talk about another way that you can see this. Okay, because so far I focused on just doing the math. Okay, how you do the calculations with the formula as it's given. Here's another way that we'll need to learn to think about it. All right. So suppose that remember I made a video. It was probably the first day of school, and it was talking about what a function is. And whether I have a formula for the function or the graph, it's really all the same information. All right. So this is a formula right here. Okay, it's an equation or a formula. And what it allows you to do is put the x in and get the y back out. Okay, plug a number in, get another number back out. But the graph is no different, right? If I draw the graph and if I label some points on it, it's the same information. Like, so here it says, well, for this particular function, if you let x be -7, you'll get y to be -1. And, well, I mean, that's true. If you let x be, so right there, that's x be -7, and this is output of -1. Okay, yeah, that is how it works. So that point's on the graph, and that information can be given to us separately if needed. And then this one says, you see that point right there? It's at -2 for x, -6 for y. So, I mean, for that function, for this being the graph of that function, it must be the case that when you put -2 for x, you get -6 for y. And sure enough, you do. That formula, that function is such that putting -2 in for x gets you -6 out for y. So it's the same information, all right? So whether you have the formula or whether you have the graph, you're given the x coordinates and the y coordinates. If we have that in function notation, then we might say like this. That is the y coordinate, but sometimes we write that like f of -2. All right. The function notation just represents the y coordinate. And then this one we would let be f of -7. All right. So as long as you understand that the formula and the graph is the same information, and as a result, we could find the average rate of change either way. If we have a formula or a graph, same information, we can do it either way. Then we're ready to move on. So let's move on then to the next question, and I'll illustrate what I just told you a little bit more. So so I put the title for this slide to be, what does the average rate of change tell us? Now, so far, I've just focused on how the math works and what the formula is, but now we'll have a context for it, and we can figure out how we should think about it, all right? Or if we calculate an average rate of change, what it tells us. So suppose that I have a curve here, and we've plotted how the number of employees in a company is related to the revenue of the company, all right? We might expect that as the revenue grows or goes up, that the number of employees also does. But how is going to take some more math, okay? Like as the revenue goes up, does the number of employees go up the same way all the time, or does it change as the revenue goes up, and so on. So the question might be, how do these two things change together? How does the revenue of a company as it grows influence the number of employees at the company, as it would presumably grow too? All right, now, so what am I given here? Am I given a function? What's f of x? It's not given. There's no formula for this. It seems like it'd be very hard for somebody to come up with a formula that would predict all of these numbers. So like we just have data. So at some point somebody could measure that, well, when our revenue was $10 billion, we happen to have 20,000 employees. That's what this point tells me right here, okay? And then as the revenue increased to $20 billion, the number of employees went up from 20,000 to 50,000. That's what this point tells me. At 20 billion in revenue, we have 50,000 employees, okay? So I still have all the numbers, even though I don't have a function to predict what they're going to be, or I don't have an alternative way to calculate what they are. All right, so let's see if we can do this. It says, can you calculate the average rate of change of employees with respect to revenue from 10 billion to 20 billion? Now, it says average rate of change, and we've already seen that. What's not given this time is a function. Because remember, when I first started the video, I said to calculate an average rate of change, you have to have a function, and you have to have a smaller value for x and a larger value for x, okay? And then here we don't have a function, right? I mean, I did say right here, the average rate of change for the function, so you'll have a function, and then you'll have two numbers. And then here that seems to be missing. But I just got done telling you that the graph is the function. Okay, so I won't put question mark. I mean, the function and the corresponding numbers are all over here. Okay. All right. Now, so here's the way that the average rate of change will be calculated in this case. All right, let's do, I know it's a fraction. I know it takes division. And otherwise what it says was the y value for the larger number. So that'd be 50 minus 20. Okay, so it's going to be this y value minus that one over this x value, 20 minus 10. Now that's the same exact arrangement as the questions we've done already, okay? That's all this turns out to be. This is the y-coordinate for this number, this x value, right? So this is y, and this is x, and then this is the y-coordinate that goes with this x value, all right? Okay, that's all it is, and that's the information as I see it on this graph. So from 10 to 20, I would do 20 minus 10 down here. And then I guess you could think of the rest, like this right here, is f of 20, right? The function value or the y-coordinate. And this is f of 10, the function value or the y-coordinate. What does that turn out to be? 50 minus 20, that's 30. Okay. And 20 minus 10 is 10, like that. Now, before I go any further, we have units here, it turns out. Okay, now I want to keep track of the units because in addition to doing the math on this question, I want to tell you what the average rate of change can tell us, all right? So here I'm doing the math, but what are the numbers? Well, okay, so what were the function values? What were the y-coordinates? Okay, well look at the y-axis. The y-axis is the number of employees we have, okay? And the x-axis is the revenue in billions of dollars, all right? So anyway, I made a little mistake there. Shouldn't be a dollar sign right there. So my units are like this. This is employees. And this is in billions of dollars. Okay, so there are units in that number. My number is 30 divided by 10, which is 3. Okay, and then I'm going to write 1,000 employees over billions of dollars. Okay, and then there's my answer. So let's think about the number and the units this way. Because as I told you, I wanted this to be an example on what the average rate of change tells me. I calculated the average rate of change here. I got 30 over 10. I added the units after that. I said up here, these are the y coordinates for the points. That's going to be in employees in the thousands. So this is 30,000 employees. This is 40,000 employees. Okay? All right. And then down here, this is revenue in billions. So I said up there, that number is employees in the thousands, and this is in dollars in the billion. So that's why, however I reduce this number, it has these leftover units of 1,000 employees per billions of dollars. Okay. Now, all right, let's think of it like this. I'm going to go back up to, I said that, well, a growth of the company's revenue probably influences the growth in the number of employees for the company. So right here, what it's saying is that the growth is like this. For every $1 billion of revenue growth, 3,000 employees were added. That's what that number reduces to, and that's what it turns out to mean. That's just between these 2 points, though. All right? So right here, I'm going to say that the growth is like we add 3,000 employees per $1 billion of revenue. All right, so now I have like a whole new appreciation for that number. If I didn't have that, it would just be the number 3, right? That's all it would be. But if I keep track of the units for the top number and the units for the bottom number, then I realize that it really tells me something. Okay? Yeah, so the company's growth phase right here was such that for whatever reason, for every $1 billion of revenue, they had a growth in employment by 3,000 employees. All right, now that's what I wanted to do. I wanted to give you an interpretation for that number. All right, now let's see what the difference is for this second part, from 20 billion to 50 billion. Okay, so let's see. I do have my numbers here. So there's 20 billion and there's 50 billion. And at 20 billion, we have 50,000 employees. And at 50 billion in revenue, we have 60,000 employees. Okay, so all right, here's what the formula is. F of 50, meaning the y coordinate corresponding to the number 50, minus f of 20, all right, over 50 minus 20. There's our formula for the average rate of change. F of 50, well, we'll have to look on the graph for that. The y coordinate associated with an x coordinate of 50 turns out to be 60. So, okay, I got 60 right there. And the y coordinate associated with the x coordinate of 20 is 50. All right, so I get 60 minus 50 over 50 minus 20. Okay, so that then is 10 over 30, right? 50 minus 20, 60 minus 50. Okay, now here we can do some rounding. That's about 0.3 with some rounding. If there's ever, like, say that you're doing a problem on my math lab and rounding is called for, it might say round to the nearest tenth or something like that. Okay. All right. So I get 0.3, but my units were the same. This is the number of employees. All right. So in the thousands. So this is 1,000 employees over billions of dollars. Those are the units. So it's like in this phase up here in that other phase, for every $30 billion of additional revenue, we added 10,000 employees. Or if you want to think about it like this, with this number, I'm going to put K employees for 1,000. And just write billions of dollars there. So for every $1 billion in revenue, that's equivalent to adding 0.3 thousand employees. Okay. All right. Now that tells us that the growth was a little slower in employment in that next phase. So let's go up here, and I want to tell you that other number was the average rate of change between 20 and 50, between the revenue being 20 billion and 50 billion. So here, that just tells me how the employment growth depended on revenue growth in this phase. Okay, so notice how I pointed to this phase here for that first part, because it was from 10 billion in revenue to 20, and now I just did the math for 20 billion in revenue to 50. So the growth is going to be 0.3 thousand employees, or add, let's do like this. I'm sorry. I want to write it the same way that I did in that first part. I'm going to add 0.3 thousand employees per extra billion in revenue. All right, so that was the growth for that other phase. I'm going to add 0.3 thousand employees for every $1 billion in additional revenue. That's how I get from this point to this point. All right. Okay, so there. Now we've done a problem where we don't have just functions, but we have a function and units to go along with it. Okay, so here this one is all about seeing the units. We did the math. I showed you how we get the units from the numbers that we got in the math, and then told you how what that tells us is a way to measure the growth in employment as it depends on revenue. All right. Okay. Now, let's do one more, because once we get to this point here where we calculate the average rate of change and we give an interpretation of it, where, here I'm saying, well, here's the interpretation of my number, is that it explains how the growth of employment depends on the growth in revenue. Okay. Sure. Now, you can imagine that for any other situation that had, some function or numbers given to us, but the units were different, then the interpretation might be different. And that's true. So if I do another problem that's not about how the employment at a company is a function of revenue, but it's about something else, then it wouldn't change the math, but it would change in how I interpret it. Okay? So let's see how that could be. Now this one, it sounds very different from the last one, but that's not going to change anything about the math. It might change how I interpret the average rate of change that I get, but it's not going to change the math. Okay? So this one says a car's moving along a straight and level road. And suppose that road has measurements marked on it, so that somebody could take measurements of where the car is at any time if they wanted to. Okay? Position and time measurements were recorded as follows. Okay, so car drives however fast it goes, and at different times its location is measured. Okay, and this is the data we're given. Maybe those numbers seem random, or whatever critique or dislike of these numbers you have, those are the numbers they give us. So we just need to understand that, for example, this number right here, whoops, time is 5 seconds, and S of t, now for whatever reason, S is normally the location or the variable that we use for position. Oops. Okay, so S of t is the position at time t. That is the understanding for that function. So at time t is equal to 5 seconds, we're at location 7 feet on the track. So here's my track. Like, there's got to be a 0 foot mark, and 1, 2, 3, 4, 5 feet, 6, 7. So that's why I wrote on there that what that means is that we're at this location at t is equal to 5 seconds. Okay, now let's read the question, see if it makes sense in the context of the lesson, and go from there. It says, calculate the average velocity from t is equal to 1 to t is equal to 3 seconds. Now, the word average, that's within the lesson because those other problems were to calculate the average rate of change. Okay, so but velocity, that's not a word that we've come across yet. So let's not worry about that just yet. Okay, so average, and then it says from, and then I'm given a smaller number over to a bigger number. All right, now, so that seems to, besides the word velocity, it seems to fit in the lesson. Let's see, like, if we can just try to do this like, other problems in the lesson and go from there. So if this is like other problems, then the way we would find the average rate of change is we would find the function value at this number minus the function value at this number, and we would divide that by this larger value minus the smaller value. Okay, so what are all those numbers? What's S of 3? Well, we understand that as the position at time t is equal to 3. So the position at time t is equal to 3 is 5, all right? So we're at the 5 foot mark on the track, right there at t is equal to 3. And S of 1 is the position at t is equal to 1. So that's this one. So we get like this. And if we do a little bit more math, 5 minus 1, that's 4. And then this is 2. Now, remember in the other question I said, well, I get my numbers, right? I can do all the calculations, etc. But these have units. They are all measurements in this problem, just like the last one. So what are these units, or what is this measurement up here? Like, what's S of 3? And what's S of 1, or whatever it is? Those are the location in feet. Okay, so what that tells me is that from time t is equal to 1 over to t is equal to 3, then we have moved 4 feet. And from time t is equal to 1, from t is equal to 3, there have been 2 seconds of time passing. You see? So this measures, it turns out, how many feet the car has moved. And this bottom number measures, as it turns out, how much time has passed. So the units are feet per second. Feet over seconds, feet per second. So my number is 4 over 2. Well, that's 2. And my units are feet per second. Okay, so maybe now you see why we use the word velocity. Because the velocity, you might think before we started that, well, that's how fast something is going. So look, if you use that math that we started the lesson with, if you just calculate the average rate of change for this function based on these numbers, you get something that has measurements in feet on top and seconds on the bottom. That formula tells me how many feet the car's moved and how many seconds it took to do it. It took 2 seconds for the car to move 4 feet. That reduces to a final velocity of 2 feet per second. All right, there we go. So now, the math wasn't so hard. I want to put a little bit more emphasis for that reason on the interpretation of my numbers. I think that's more important. So let's repeat this for up to times t is equal to 3 to t is equal to 5. All right, well, so that wouldn't be any different. We take the function value at this number minus the function value at this one, and we divide that by this number minus this one. Okay, so what were the function values? What's s of 5? That's my position on the track at time t is equal to 5. That's 7. You are here at the 7-foot mark when t is equal to 5 seconds. All right, and then s of 3, okay, that's this number. That would be your position at time t is equal to 3, so that's 5. So we are at the 5-foot mark when t is equal to 3, and I get like so, and I get 2 over 2. Now, again, what were what's the meaning of the numbers? Like, what does s of 5 and s of 3 tell you? That tells you the position in feet. So this is 2 feet, and down here, 5 and 3, t is equal to 3, t is equal to 5. That's my time in seconds. So this is 2 feet in 2 seconds. Okay, which reduced because 2 over 2 is 1 foot per second. All right, there we go. So it's going a little bit slower than in this other time period. Okay, all right. Now I can summarize and report information to you in lots of ways. I think the last thing I'll do, I think it's worth saying that, like, as with any moving object, even if you think it's a little weird for a car to be moving 2 feet per second or 1 foot per second. It didn't say what kind of car this was, so we're not going to question that. Here we're moving at 2 feet per second. That's in this interval. And then in this other interval right here, from 3 to 5, we're moving at 1 foot per second. Okay? All right, slowing down, it seems like. Now, we'll learn a way in the next lesson to refine this to be a little bit more precise, because maybe you can imagine that unless this time period right here is very small, the average may not be accurate. Okay? So I'll give you a quick example as something to think about in order to understand where we'll take this. Okay? So I think like 2 seconds might not be small enough to actually to accurately measure the speed of something. So when I used to have to drive to school, so say I drive to school, and one day I was kind of curious, and I measured how long it took and how far it was. So at that time, I lived pretty far from school. And so I drove 36 miles to get to school. And it took me 45 minutes, which is 0.75 hours. Okay? All right. Now, so notice if I treat this like that up there, and I divide these numbers, and I see that I get leftover units of miles per hour, look at what it says. So if I take 36 divided by 0.75, turns out to be 48. So my number, okay, so this is just like what we're doing up there. This is an average rate of change. Okay, then my number turns out to be 48, and my units happen to be miles per hour. Okay, now can you tell, like, that number is not really accurate about my speed at any particular moment, because at any particular moment I was probably going faster or slower than this. I probably had to speed up, stop at stoplights and stop signs, maybe cruise on the highway part of the time. If there's traffic, I have to slow back down. This is really just an average. It doesn't tell me anything specific about what happened along the way. So neither do these, it turns out. You know, this tells me in that time period from 1 to 3, this is on average what the motion was like. It doesn't tell me anything specific about what happened in the middle. All right, so we need a way to refine that, and we'll do that in the next lesson. And we'll find that the most accurate way to measure rates of change is to make this down here as small as possible.